conclude what we had started yesterday on our analysis of 3-point functions, correlation functions, in a particular sector, in this so-called SL2 sector, in any closed force of preeminence. So, one of the things I wanted to highlight is that we have these 2 points of view. We can think of them as one being kind of an experiment and the other one being kind of our theory, where on the one hand, we can take 4-point correlation functions that are very well-defined objects. You just put some 4 external operators being some BPS operators, like the ones drawn here. This is 2z's 1x, 2z's 1x bar, 2z bars 1y, 2z bars 1y bar. You take some very simple correlation function of BPS operators. All of them are finite. You just compute the 4-point function. You start computing them at loop level, and there has been a huge development in computing correlation functions of 4 BPS operators at loop level. For example, these recent works of Koshemsky, Sokachev, and collaborators exploring some hidden symmetry of these correlators. So there is a vast amount of data, of experimental data, that we can take, very pure experimental data, from these BPS correlators. What do we do with this data? We expand it out in the OPE, we expand out what flows, and we analyze what flows by decomposing it into conformal partial ways, into these conformal blocks. And by seeing what flows, we learn several things about what is flowing. And in particular, you can learn about sum rules, about what is the value of the average of the square of 3-point functions for a given fixed spin. You sum over all primaries, these are all solutions of Bethe equations. You compute the square of the 3-point functions at tree level, and this is what we extracted by some tree level computation like this one here. If you would go to loops, you would start correcting everything, and in particular you would be able to extract the correction when one is at tree level and one is its one loop correction, and so on. So you can easily extract this. Of course, you could wonder whether you could try to extract a single 3-point function. How could you extract a single 3-point and not sums of 3-point functions? And in principle, you could, but you would have to work a bit harder. For example, we have been fixing the external operators. So suppose you also play a little bit with changing the external operators, then you will get different sum rules. And you remember, for example, for spin 4 and length 4, if I remember correctly, there were 5 solutions. So if you try to work out 5 cases, 5 sum rules that contain these 3-point functions, you can probably solve for these 5 structure constants. So you just have to consider more, you have to engineer clever choices of external operators such that you generate different sums, and from those sums you could try to probe individual 3-point functions. The other point of view is you say, no, this is what is physical. What is physical is where this sum over all states, I mean, after all, who cares about some particular state in the middle of the spectrum? And then you should proceed differently. Then what you should do is, you take these sums as your goal, and you can go from the other direction, from what I was calling here the theory. You start with integrability. Each operator is a set of Bitterroots. From each operator, we map it to a spin chain, and we compute its structure constant by working out a bunch of scalar products of spin chains, just a bunch of overlaps of spin chains, and we sum them up, and we compare with this integrability data successfully, as we saw last time. Okay? And then the question becomes, why are these sums some nice objects? What properties do they have? How can we try eventually to compute these sums directly in perturbation theory and so on? Now I will use the projector. It was good as well. Okay. Any question here concerning the summary? Huh? Okay, very good. So, now, now I would like to describe a little bit, as I promised. I wanted to try to broaden up a little bit at the very end. And the idea is to try to see what else we could do to broaden what we have done so far. So far we consider the operators in a so-called SL2 sector. SL2 sector means that we have an excitation trace of a bunch of these and then some derivatives that are moving on the C of scalars. Okay? There are other sectors that have the same very simple interpretation as a single kind of particle moving in the sea of scalars. These are called rank 1 sectors because there's only one kind of particle. For example, perhaps the most famous one is the so-called SU2 sector, where we have trace of scalars and the other excitation that is moving is an X field. This is perhaps the most famous one, where we think of the Z as a spin up and the X as a spin down, and this is just an SU2 spin chain. So this is a non-compact spin chain. So this one is what we have seen. It's a non-compact SL2 spin chain. This one is just a standard XXX spin chain. So definitely we also know a lot about scalar products in this spin chain and so on, so we could also try to compute 3-point functions in this case. And there is also a fermionic version of these two, which is the SU1/1 sector, where we have traces of Z's and of a fermion excitation that is moving in the sea of scalars, and this is a super spin chain. I don't know, it's fermionic XXX. And then we can start mixing things together, and then we can start going to higher rank sectors. Yeah, like starting to put SO6 or fermions and scalars and derivatives together and so on. So, apart from some very particular cases that even in practice boil down to rank 1 sectors, nothing is known about higher rank sectors. And the reason is because very, very little is known, apart from some very simple cases, as I said, very little is known about scalar products for higher rank spin chains. So this is kind of an open problem in integrable models. If I give you, say, instead of an SU2 spin chain, an SU3 spin chain, and I ask what is the analog of Slavnov scalar product, which is a scalar product between an on-shell beta state and an off-shell beta state. Many people think that the best you can write is a huge sum over partitions and that there is no beauty and nothing simple to be written down about higher rank spin chains. And truth be said, no one found it yet, so maybe they are right. So maybe it is really much, much more complicated. I find that very hard to believe because n equals 4 normally there has been no obstacle up to now in going from rank 1 to higher rank. Bit equations were easy to generalize. In the computation of amplitudes, there is no big issue with starting to put a lot of R charge in the game. So it's a bit kind of mysterious why here for 3-point functions people are struggling so much, and it has been kind of a big, big obstacle to consider, for example, 3-point functions involving all the scalars of the theory in a generic setup. And this is just because scalar products, the same kind of scalar products that we were writing yesterday, are just not worked out for these higher rank sectors. But still, we could try to understand first these 3 sectors, maybe in the hope of understanding what they have in common and trying to put them up together and getting then the full thing. For the spectrum, partially it was more or less how it happened. People had knowledge about these 3 sectors separately. There was then a very nice paper by Matthias Staudacher where he tried to understand how to write them down in the same language using this picture of S matrix of excitations that scatter. And soon after, Bizert and Staudacher came up with a set of equations that describe the full spectrum for all the sectors and that reduces very nicely to the 3 rank 1 sectors and then meets a whole bunch of symmetries that match the 3 rank 1 sectors between themselves and so on. So it was really very important. So let's try to learn at least as much as possible as we can in this problem in the hope that this will give us some inspiration to get the full analog of the Weiser-Staudacher so-called Bethe equations for the spectrum, here for 3-point functions. So actually I think you were right in raising the screen, but because I do have something behind it and I want to keep this backwards. Okay, so let me just remind you, so for SL2, I have here in the blackboard some things that are known for this rank 1 sectors. So let's start by SU2. So SU2, you can have two different kinds of fields, Z's or X's, and the rest I don't need to label because you can just follow the lines to see what they are. If you have an X, it must be contracted to what? What field? To an X bar, and a Z to a Z bar, and then this is an X bar to an X, and this is a Z, this is a Z bar, and so on. So here is a correlation function, and one thing that is immediately a little bit, it's immediately obvious, is that it's not very symmetric. Okay? This is a fact of life. It's not very symmetric with respect to the three operators, but if you want to make a spin chain which is SU2, which is made out of SU2 spin chains only, and which is not extremal, to avoid this mixing with double traces that we discussed yesterday, this is kind of the most natural setup. Even though I heard there are people working on other possibilities just within SU2. Okay? And we could consider again the simplest possible case where two of them are BPS, two of them are just rotations of the ferromagnetic vacuum. Just start with Z to the L and rotate a couple of spins. So these are just very simple states. And this one could be a non-BPS state parameterized by a set of Bitterroots. Okay? What do we get? We get again a A over a B, where A is related to the scalar product with the vacuum, is a sum over ways of partitioning the roots in two sets, and then there is an interaction between the two sets with a function f that takes this form to leading order. Just this 1 minus I over U minus V. Okay? I remind you this was exactly the same we saw yesterday for SL2, except that there was a different sign in F. Okay? This different sign here for S was what we found yesterday for SL2, and here there is a different sign. This is typical. SU2 and SL2 to leading order are often related by just a simple shift of a simple change in some sign. It is just the difference between SU2 and SL2 is being one is a compact representation, the other is non-compact, and it's very common that you just tweak a few signs here and there and you go from one to the other. What about B? What appears downstairs? It's exactly what we saw yesterday as well, as the so-called Godin norm, where here you have the S matrix. The log of Bethe equations, and in particular the S matrix. Now, one of the things that is quite nice about SU2, so what are the plus of SU2 versus SL2 versus SU1/1? So let's start analyzing that a little bit. One of the nice things about SU2 is that a lot more is known about the spin chain at loop level than it is for SL2. For SL2, as I said, we don't even have the Hamiltonian in a workable form. We have an Hamiltonian, but it's a mess to work with. And we don't even know the form of the wave functions, the correction to the wave functions exactly. We know these contact terms for the first 4 particles, but we don't even have a general formula. This is not true in SU2. In SU2, the wave function at one loop plus the correction at 2 loops is well known. And we can even use algebraic Bethe ansatz or some modification of algebraic Bethe ansatz, something, to study this wave function. So this is a big plus. We have formulas purely within algebraic Bethe ansatz for studying the corrections to the wave functions in SU2. But at loop level, I told you it was not just about correcting the wave functions. It was also about considering Feynman diagrams. You have to correct them by doing loops. And when you do loops, there are 2 types of effects. You see, clearly, the loops can be something like this, which is really related to the splitting of the operators, or they can be something internal here. And you might suspect that these guys are more important for correcting the 3-point function than these ones here that don't look very much like correcting anything related to 3 operators. And indeed, if you analyze it carefully, you see that these operators are actually correcting. You remember that this object here in space-time, it has a 3-point function, a structure constant, and then some anomalous dimensions appearing in the exponent. And indeed, these kind of diagrams, they are rather correcting the anomalous dimensions that appear in the space dependence. So they are rather contributing not to the structure constant that we are interested in, but rather to the correction to the anomalous dimension, which makes perfect sense. These diagrams there are associated to the propagation from one operator to the other. It makes total sense that it is more correcting the propagator between those 2 points. Okay? And these are the kind of diagrams that effectively contribute to the structure constant. And when you sum them all up, you sum this one up, you sum the one where the scalars interact with the contact interaction, and so on. And at the end of the day, the net result of summing all of these diagrams up, so you sum all of these diagrams at the splitting point. This is a contact interaction, and so on. And at the end of the day, what this amounts is to saying that in your spin chain language, you had your spin chain, and you were breaking the spin chain and so on, and now you should do one extra thing. You should insert here some kind of quantum gate, some kind of operator. Think of this as a bit like an Hamiltonian density. Let's call this a splitting operator, something like I plus 1, that takes on sides I and I plus 1 where the spin chain is splitting, and goes to sides j and k of 2 other spin chains. And we have to work out this splitting operator. So all these sums of diagrams end up constructing a kind of splitting operator, and the prescription now at one loop is correct the wave functions on the one hand, but then what you have to do is not just scalar products, it's scalar products with the insertion of this splitting operator in the appropriate splitting points of the spin chain. Okay? Is this clear? So the problem again, once you compute the splitting operator, you can forget about Feynman diagrams. Then everything is well defined once more. You are instructed, construct the state for this wave function, which you now know. But now, instead of just overlapping spin chains, insert splitting operators at the splitting points that you computed once for Feynman diagrams, and you compute once and for all. Like the Hamiltonian, you compute once and that's it. Then you forget about it. Is it okay? Then you forget about Feynman diagrams. So this is a big advantage because it means that without any assumption we can derive the one loop correction and start seeing some structure. There's no guessing, there's nothing. You can just derive. And here is the result of what you get. And what you get is kind of very nice. You almost don't need to touch what you get at one loop to get the two loop result. Sometimes I oscillate between one loop and two loops. It's always confusing even for me, because what I call a tree-level structure constant is the structure constant to leading order, but it uses the one loop wave functions, the wave functions from diagonalizing the one loop Hamiltonian. And what I call one loop structure constant uses the two loop wave functions. So please don't be confused by that. So the sub-leading result, let's say like this, then it's safe. The leading result was computed just by scalar products, and the sub-leading result is a very minor effect. For example, here in the goddamn norm, you add bit equations, and all you do is you replace the S matrix by the corrected S matrix with the two-loop correction as well. So that could not be more natural, it's super natural. You just replace the goddamn norm by the quantum goddamn norm. What about this A, this mathcal A, which was given by this? Again, all you have to do is deform this F, and you add some small quantum correction for this function of U and V, this interaction. And then finally, you dress this up by a very simple prefactor, which is 1 minus the anomalous dimension, the energy at one loop, basically what this function spectrum that we had in Mathematica was given, over 2. And this, the claim is, computes this structure constant at one loop. So there was 3 level and here is one loop. So the claim is, if you take this and compare with some experiment, with some data, some correlation function, it will work. Okay? Any question here? Yes?
In fact, the propagators which can connect to fields from the space operator. Not the part of the spin chain, but maybe the part of the spin chain with the PS operator. In the right corner of this.
Here?
Yes.
So this would be a splitting operator that would act on this spin chain instead of this one here. So you have 3 spin chains, and you have how many splitting operators? You have 6. Because you have one here, one here, and the ones on the outside. One here, and one here. So you take three spin chain states. The simplest thing is you take three spin chain states, psi. And now out of each of them construct psi prime. What is psi prime? It's psi after acting with the splitting operators in two positions. Now you have three states. Three psi prime 1, psi prime 2, psi prime 3. Right? Now with these three states, do the usual weak contractions. Same thing as at 3 level, because you already took care of the loops. Yeah? So again, what I just said is you start with some state, say the state of operator 1. You construct 1 plus the splitting operators, the two of them acting on 1. This defines some operator 1 tilde. And then you do the correlation function of 1 tilde, 2 tilde, 3 tilde, as if it was a 3-level computation. Take the 3 spin chains and contract them as if it was just a 3-level computation. The spin chain overlaps. Of course, this is tricky because by acting with this operator, if this was a nice beta state, this is not a nice beta state anymore. So if the scalar product was nice before, you are not guaranteed that now you still get nice scalar products because you screwed up a little bit locally. This is a local operator. But this, locally, close to the splitting part, doesn't really look like a beta state. It looks a bit different. So you might wonder whether you will be lucky and whether the scalar products will still have some nice beauty after doing this operation. And the claim is that yes, and that in this particular SU2 case we can derive y and understand y even algebraically because the wave functions are under very good control. And because people computed the splitting operator, I should have said, people computed this by Feynman diagrams. Okuyama, Feng, and Roy van Aldai. There are a few papers of people that computed this splitting operator. Any question here? Yes?
You mentioned that there is a good control over the wave functions by some algebraic methods. Can you say a couple more words about this? Is it a generalization of algebraic based ansatz?
Yeah, there are several approaches that work in order to construct these states. The one I like the most was something we proposed with Kolya called the Teton Marxism. And the Teton Marxism is just some generalization of the algebraic bit ansatz. If you remember, in the algebraic bit ansatz, you had some construction of creation operators B out of a monodromy matrix that was represented like this, pictorially, right? This was the algebraic bit ansatz construction. You had some monodromy matrix like this. Is this notation clear? Yes? And here you had some rapidity U, and here, were there some inhomogeneities here? Some parameters here? Did Ko use some parameters? If he was doing form factors, probably he did, no? But you know that we could put some rapidity here, theta 1, theta 2, up to theta L. Now this is a non-homogeneous spin chain, if you put some parameters here. It's definitely not what we want, so these guys better be all the same. And indeed, to leading order, they are just 0. But what you can do is you turn them on, you do some kind of funny operation with them, and then you put them to 0 at the end again. So it's kind of simulating quantum mechanics. It's like quantizing, putting higher loop effects by taking the still 3 level, putting some impurities, doing some noise with these impurities, and then putting the impurities to 0, and it looks as if it was real quantum mechanics. Had the AVA picture, but it's correct. Now this works for SU2 technically for the reason that the S matrix is not corrected at loop level in terms of rapidities, only the dispersion is, and it's relatively simple to quantize it by this cheap trick of putting some impurities. Now for SL2, this is where we would like to quantum correct our result. This is where we like to do it. First of all, because there is much more data, because as we said, whenever we have a correlation function, we will have SL2 operators flowing in the middle. There's no way out. SL2 operators will have infinite towers of them and so on. It's where we have most data. They are definitely the most important operators for constructing correlation functions. But here we have two problems. Delta psi is not known. Head phase. And this splitting operator was not computed yet. So it's kind of annoying because the two main things that we would need are just not known. So what are the options here? One option is of course to wait, to try to convince people to study these two problems. But the other option is to just look at the two blackbirds and see they are so similar, probably we can guess the result. Okay? So what would it mean to guess the result? For example, this A over B. B was the same for SU2, but with the S matrix of SL2. And here what we were told to do is to just take exactly this, even at loop level. So let's try the same. For B, let's try to keep the same B as we have, but just put the corrected S matrix at one loop. It's natural to try. What about for F? Well, for F, let's correct F a little bit. Let's put some correction to F. Let's parameterize it with a few parameters. And let's try to fix the parameters by some data, and then check if it works. And is it all? Well, maybe we will have also to put some kind of prefactor, some one-loop anomalous dimension. Let's put some parameter omega here, and this guy is to be fixed. Hopefully, if all works. So we could try to do something like this. 1 plus delta F, try to fix this later, and so on, and here correct the S matrix. Okay? And then try to ask, does this work? And if it does, is it inspiring and can it help us go beyond it and go to even higher loops? Okay? So here behind this blackboard I have SU1/1 that I think I will leave to the end. And now let's go to Mathematica again and let's play this game, which is kind of probably the trickiest part of the notebook in case you have seen it in detail, which is let's analyze the experimental data that we have for now, a correlation function, not at 3 level but at 1 loop, and see if we can take our simple result that we have derived, modify it a little bit in the simplest possible way with some few parameters, and try to see if there's any chance of reproducing this data. And of course it will work. Okay? So, but before okay, in this minute while it prepares, we should ask what could be. So, what is the hope? What is the hope in this program? The hope is that maybe we are already kind of close to the all loop result, to the structure of how the result looks like at all loops. The hope is that if all you have to do is take this B and put here the all loop S matrix, which is known, and take this A and correct this F and find some all loop expression for this F. And then hopefully this prefactor is simple enough that we can also guess. Hopefully this is the easy part. Here I don't have any guess for what the next term is, but this looks much simpler than everything else. So this is the hope. The hope is that the all loop result for a structure constant, it has some easy part, and then it has an A and a B, B being also very easy. Hopefully it is just a Godin norm. And A hopefully is parameterized by a function F that we have to bootstrap at all loops. And the idea is to try to find what is the principle that fixes this function F. What are the kind of equations that this F should obey? And one thing we realize here is that it obeys some kind of a nice property so far at 3 level and for SU2 at 1 loop, which is that F of UV divided by F of VU is equal to the S matrix. It's kind of a nice axiom. It's very similar to it's the same as the axiom that you saw in Benjamin's lecture for the pentagon transitions. And it's kind of natural to try to promote it to a postulate, to an axiom. Let's try to see if this is kind of a natural guess and a natural property. And in fact, it is almost a property that we can derive by several symmetry reasons, and I can tell you more about it later. But for now then, let's go and try to play this game. And again, my main goal here is to give you, as I said, all the necessary material such that you can then play and do one more loop yourselves. So the first thing is that we can take an experiment and read off this data, this P10 and P20 that I wrote there. You can, and that I'm covering now. You can predict these sums. So the ones we are interested in are the 0, 0, 1, 0, and 2, 0. Okay? So what is 0, 0? 0, I should call it 0, 0, not 1, 0. 0, 0 is what we computed yesterday. Remember, it's the sum of 3-point functions. It's 7, 15. Are these numbers familiar? Do you remember them from yesterday? The first line was what we saw yesterday for L equals 4, spin equals 4, was the sum of structure constant squared for at 3 level. The correction that contains 3 level times 1 loop is this P10. It should contain these numbers here. So again, this is just, we take some correlation function that Sokachev and friends computed. In this case, Sokachev, Aryutinov, and friends. We take this 4-point function, we expand it in the OPE, we read off the structure constants. So this is what we should get. This P10 is what we should get for the correction to our sum of 3-point functions squared. And I want to point out that we already have data waiting for us for the next correction, this P20. And I have nothing to say about how to match this from integrability, but here is a set of predictions. We have all this beautiful data, and it is just waiting to be understood from an integrability point of view. You see, this line P20, we should understand this line P20, this last line. It is just the next correction, the structure constant. It's waiting here to be in a very clean, already processed table. So let's go and try to see if we can get these numbers, -8, this third row. So what do we have to do? Well, the first thing we have to do is find the corrected Bitterroots. So we had the Bitterroots at leading order, and now we need a corrected Bitterroot. So we need to solve bit equations again, but now not to leading order, but to subleading order. So we had a spectrum that gave us the position of Bitterroots, uj. Now you need plus g squared delta uj. We need a correction to the Bitterroots. But the correction is much simpler, actually. The hard part is to do the leading order. Because once you do the leading order, first you have this Joukowsky variable, remember, which was u plus u squared minus 4g squared over 2g. And when your series expanded, this is just u over g minus g over u, which is what I wrote here in this line. Okay? So this is just the expansion of Joukowsky to leading order. And what were bit equations? Bit equations were what is written here. This is in the form we wrote on the first day. There is this factor x plus over x minus to the L, which is the momentum. And there is this factor, which is the 3-level S matrix, and this, which is the correction to the S matrix. And there is a product here. Okay? Is it clear? Why did I try to format it? I don't know. It's okay. Is this okay? So these are the equations we want to solve. And now I'm not taking any log and going to arctangent or anything like this, because now all I have to do is I replace u by what we found before. Remember this UL, LS, so if I put 4, 4, this is what it is. These are the Bitterroots at leading order. I replace them by Bitterroots plus delta Bitterroots. And I take the coefficient of g squared of these equations. Because the g to the 0 will be 0. will be satisfied by the leading order expression. So I take only the coefficient of g squared. Is it okay? And now, by definition, this is something linear. By definition, this is linear in delta u. So not just a linear equation, so you just solve it. Okay, that's it. So we can ask what are the u's at loop level, say for length 2 and spin 2. And let me do /n so that you can see better. And here are the Bitterroots corrected, you see. There are 2 Bitterroots and they are correct. And we can ask what about the ones we wanted, 4 and 2. Now there are 2 sets of Bitterroots and here are they with their correction. Okay? Is it clear? Should I debug a little bit or is it okay? It's okay? Okay, very good. We could do 4, 4 and so on, and we'll get all these Bitterroots and solve with very high precision. Okay, so we take the first solution with length 4 and spin 4, and here are the Bitterroots and its corrections, you see, with 150 digits. Okay, very good. So this was the easy part. Now, this is even easier. Now what we have to do is just take derivative of log of bit equations. Here are bit equations, I just copy paste them from above. Here is the log, I put a log, I take derivative with respect to uk. Okay? And what we are instructed to do is take derivative not with respect to u but with respect to p, so I have to divide here by derivative of p with respect to u. This is just change the variables from p to u. Is this okay? So this b loop is just the one loop result. So I can show you, for example, if you have b loop length 4 applied to the roots 4, 4, the first set of roots, this gives it. So this is the norm, and if you remember, let's check. Let's compute just b, and let's do without loops, and the first number, you see, the first number agrees, and then there is the correction here. Okay? Very good. And now comes the more interesting part, to find the quantum, this A. And this A here, I just wrote exactly what we have before, except that instead of writing explicitly what this F is, I put an F here, and an F here. So if you look at the previous section, before it was exactly the same thing, but this F was something explicit. Let's see if I find it easily. You see, it's exactly the same thing, but here we had something explicit for F. And now we are putting F, which is not known. Is it okay? So let's close it. And now we put this F here. And this F, we know with two leading order. It is 1 plus I over U minus V. And we don't know it is sub-leading order. So let's try some guess. And here is the guess that I want to try. And let me explain why. It looks a bit strange, but it's the most natural one. And it was the first one we tried, so this was really copy-pasted from a notebook we had. So what is the guess? We want F over F to be the S matrix. So the last factor first has nothing to do with S matrix because it's symmetric in U and V. So if I divide the last factor by U and V exchange, I get 1. So that last factor is blind to this relation. But we put it here because it was there in SU2, and also in SU2 it was blind to this relation. So let's put it because if it was there in SU2, why not in SO2? And in SU2 it was derived, I recall. Okay? So let's put it with some gamma that we have to fix. That gamma is a number we'll have to fix later. And then the S matrix, you see the S matrix there. Where is the S matrix? It's in the previous line. Contains this extra factor here. You see it? It's 1 minus x over x and so on. So it is natural to put just the numerator of it or just the denominator or to put without the 2. So we can put a little bit of numerator, a little bit of denominator with some beta 2 minus beta and minus beta. What do you think is most natural? I would say it's beta 0, 1 or minus 2. Or beta 1, sorry, beta what? 2, 0 or minus 2. Right? No, 2, 1, there. Okay. What's most natural is to have 2 minus beta be beta 0, 1 or 2. You agree? So if beta is 0, it means that we just put numerator. We take from the S matrix just the numerator. It's half of the S matrix. It does obey this relation. If beta is equal to 2, it has just the denominator. It also obeys that equation. And if beta is 1, it's kind of more democratic. We take, instead of the square, we take half of it. Okay? So can someone try to guess if any of these natural choices is correct, and if so, which one? Any preference? We'll see. Okay, and that's it. Okay? And now we write the quantum 3-point function. We have again the energy as before, and what we do, we put 1 minus omega over 2 times the energy times this loop stuff. So again, let me emphasize, how many parameters do we have? We have omega appearing in the energy, we have gamma appearing here, and we have beta appearing here. So we are trying an ansatz with 3 parameters. But it's not a lot, because how many points of data do we have? Infinitely many. We have an infinite tower for length 4 and spin, any spin. And after checking that, we should go and change the length and check again and so on. So we have infinitely many points of data for 3 parameters. It's okay. Especially if these 3 parameters don't turn out to be 17 over 13 or some crazy numbers. So let's try. So we write this. And so let me show you. So if I have now C1, 2, 3 at loop level, spin 4, this splitting in 2 with 1x and 1x bar upstairs, and I put the loop roots for the first one, the first solution to Bethe equations, and I would get this. Okay? You see there is the 3-level part, which is the same as before. Hopefully, if we did no mistake, let's check. So before it was C1, 2, 3 only, and we don't put loop here. So the first number is exactly the same, and now we have a proposal for the correction, which is parameterized in terms of 3 numbers, beta, omega, and gamma, that we want to fix. It's okay? Okay, so now we do it. What we do is we just compute then the sum of the square of all 3-point functions for spin 2, 4, 6, and 8. Okay. And here we put some dynamic to see which Bitterroot she is analyzing, to see that it is changing, and what spin it is. Now it takes a bit longer. It is doing all that we did before. It is solving bit equations first, then solving the corrected bit equations, then plugging into those expressions, then expanding them in perturbation theory. It's doing a lot of things, but it's relatively fast. So now it's in spin 8 already. 8 is covered by the mouse cursor. And it is generating a table, and then it's rationalizing. Hopefully we will have enough precision and get just a bunch of rational numbers. And here is what we expect from the data. Let me go on while this runs. This is what we expect from the data. We expect at spin 2, let's look at this table. Where is the data? Data here. Let's copy this table and go down. From the data, you see here I just wrote what is in this line. Minus 8, minus 196 over 81, this one. Then this big number is this one here, and so on. Okay? So this is what we expect. And here it's computing, so we have to wait a little bit more. It's going through all the solutions at spin 8. There are maybe 12 solutions or something like this. It should be almost done. This is the next to the last, I remember. This is the last, I think. There's one more. Okay, this is the last for sure. Very good. And here is a set of predictions. You see, at loop level. We have at 3 level what we expect, and then we have a bunch of rational functions times gamma, beta, and omega. Because we did rationalize, so it became just a bunch of rational numbers. And this is what we expect. And now we ask, okay, we have, for example, here how many predictions we have? We have 4 predictions and we have 3 parameters, so it's enough to fix. So we can take the first 3 from each of them and equate them. So, and we have an equality, and we can ask logical expand. So if 3 things are equal, each of them is equal, and this generates a set of 3 equations for beta, omega, and gamma. Is it okay? And now we solve. We ask to solve this equation. Right? And this is nice. Right? We could be getting beta equals 13 over 7, and so on. We have this These were the equations again. And this is kind of good news when beta, gamma, and omega have these nice values. Okay, so perfect. So we have this replacement. Beta goes to 1, omega, gamma goes to 1, omega goes to 1. We can now compute our f. So this is the correction to f at one loop, it seems. You see, this was it for SU2, and this is what it is for SL2. It's a bit more complicated. It's a bit different. Not more complicated, I'll say it's just different. And now we have the final check. We check the first 3 points. Does this number come out? So we just replace, and we compare data and prediction, and the last number, now without any free parameter, comes out perfectly. And we could now put more spin or check other lengths and so on, and it would work. So the conclusion is we did not check directly the 3-point function. It would be awesome if someone would be brave enough and compute this 3-point function by Feynman diagrams with just one single 3-point function and then match against what we are predicting. This is not available. What we matched was again some rules. We said to solve bit equations, sum up all the solutions. So we are not checking directly one object only, but rather a sum of them. But still, we are checking many different sums and so on. It seems very likely that this is correct, so it's very natural to conjecture this result, that it is indeed, that the result is indeed of this very nice form with an f that is correct. And now, the temptation is, of course, to ask oneself whether is there any set of axioms, any set of rules that this f should obey that we could use to try to fix this f. And both in SU2 and in SL2, we actually had some kind of arguments, but these were kind of a posteriori arguments. After we knew what the result was, we came up with some simple arguments to try to argue why it is in this correction. For example, let me give you the argument for SL2. So the argument for SL2, how we could derive this expression for the correction for f, could go as follows. So the first thing to have in mind is that we had observed before this ultra locality for the wave functions, for the correction to the wave function. Namely, the contact terms, we only had contact terms. We only had to modify the wave function when magnets were on top of each other. Okay? Because of that, it is probably natural to think that the splitting of the wave functions, the breaking of the wave function in two, here is milder than in SU2. In SU2 we had contact terms when two excitations were close to each other. Now we don't. So now when we break, even at one loop, it is still kind of a safe procedure to break. From the contact terms point of view, you don't get entanglement between the two spin chains telling us that the spin chains were broken or not. Okay, so why am I saying this? Because this leads to the idea that if this is true, what we could say is let's try to impose that A0 is equal, which was equal to AL should be equal to 0. Remember? This was kind of the, why should this be true? Because as you remove L, or if you put L to be the full spin chain, you are constructing kind of a scalar product between a non-BPS operator and a BPS operator, and it should be orthogonal. So they should be 0. And I think this ultra locality is an important thing, because if it was not for this ultra locality, this would be a tricky thing to do. Because as you are shrinking, it's never true that you are getting just a scalar product, because there was some connection between the spin chain, and it will not disappear as you take L to 0 or L to be very large. And you can see this because it is not true that this relation is true in SU2. So I think it clearly, it should be, either it's a coincidence or it is related to this kind of ultra locality. So I want to claim that this ultra locality is what allows us to say that we want this at loop level. Because at tree level it's definitely true, we argued already why it should be true, it's just orthogonality, and it is true indeed. But let's suppose we want to impose this at loop level. And let's suppose we do it for two particles. We want to impose that A0 for U1 and U2 is equal to 0, and the same thing for AL. So let's write what this is. So we get 0 equal to, from A0, what is this? It's 1 minus f of u1, u2 minus f of u2, u1 plus 1. So let me explain. So let's see that it works. So alpha and alpha bar, when you have two particles, what can be alpha? It can be empty set, full set, or one of the others. If it is empty set or full set, then we have nothing here in this product, because alpha is either empty set or full set, so alpha bar is empty set or full set, so here we have nothing. And here, if alpha bar is empty set, we get 1, but if alpha is full set, we also get 1 because of zero momentum, because total momentum is 0. So if alpha or alpha bar, so these two, this 1 and this 1 are those cases where alpha and alpha bar are either the empty set or the full set. When alpha is either the empty set or the full set. And when alpha is one of the Bitterroot and alpha bar is the other, we get just f. And remember, L is equal to 0, that's why we have no momentum. That's why we have no exponential. So this is kind of an equation that we could impose. Another equation is when L is equal to 0, when A is equal to L, and we will get 0 equal, here we'll get still 1, here we'll get the same, f of u1, u2, times e to the minus I p2 times L, minus f u2 u1, times e to the minus I p1 times L, plus 1. Equal to 0. Just the same thing, but now L is not 0, L is capital L, so we have this extra exponential. And this factor here, by Bethe equations, this is just S of, okay, Ben would know, and I of course don't know. I will try randomly. Is this correct? I don't know. Either this or 1 over this, doesn't matter. I will try to do it carefully. E to the I p1 L S of u1 u2 equal to 1. So if I put a minus here, I put a minus 1 here. So if I put on the other side, I put plus 1. So it's like this. So e to the minus is 1. You see? It's always wrong. I think I never ever got it right yet. Okay. So you can replace them by this, and now you have two equations. They don't depend on L anymore after you use these Bethe equations. And these two equations imply that f is equal to 2 over 1 plus the S matrix. Okay? And in particular, this relation implies that f over f equals S matrix. It implies that relation. In particular, it implies that. Conversely, we could have forgotten about the second one and used this one plus that equation. But you see here that just imposing that in the right limit the result should vanish, we fix f to be this. And if you take the S matrix and expand it, sure enough, you do get exactly the correction to f that we wrote, that we found, that we derived. Okay? For SU2, the argument for fixing this A was kind of funnier. It was saying that A, this was for SL2, and the argument we had for SU2 was saying that if you have A, 1, so length 1, and you put two particles, this is equal to 0 because they don't have enough space. Because you cannot put two x's on a spin chain of length 1. And this also fixes f to be the correct f for SU2. Okay, but this is kind of just hand-wavy argument. Of course, the main goal is there some kind of bootstrap program? Is there some kind of principle that fixes this f to all loops? Is there any kind of hope that this kind of sums over partition has some meaning at finite coupling, in particular at strong coupling? Is there some strong coupling version of this? Can we take some kind of classical limit of these expressions and take analog limits at strong coupling and try to find some common structures? And these are all things that are being investigated. As I said in these lectures, I tried to focus on one particular topic. So I was recently in the south of Portugal digging holes in the sand in the beach. And one awesome way of digging a big hole, there are two ways. One way is to dig a huge hole and you draw a perimeter. I did both ways, of course. So you draw a perimeter, then you take out a lot of sand. This is like having a big introduction, a broad image of the field, and so on. And the other option is you forget about it, you just dig a very, very thin tunnel until you reach water, and then you keep digging, and water starts digging the hole by yourself, and then sand starts falling, and you have to take it out, and you end up broadening just like the other way, but it's just another way of doing it. And here what I try to take to help you is to help you dig this hole and reach water. So this is as far as people know about correlation functions in one, probably the most important sector in ADS-CFT, this SL2 sector. This checks of data is the best there is. There is more data to check. So there are many other things to do, but now you have all the tools, I think, to start broadening this and learning more. So here is just a list of some things. We have this tool of data as well, as I said before. What to do with this? Well, here's a comment. It contains zeta 3, for example, which is kind of funny. And the first, but this zeta 3, I think I think the zeta 3 will just correct this omega. I think this omega will be 1 plus some zeta 3, and that's enough to account for the zeta 3 part of this table. But what else? Can we get it? Can we find a guess? Can we generalize this guess and guess the two-loop quantum deformation? How to derive all these guesses? Is there some principle? Is there some set of series equations, some kind of bootstrap that allows to determine? Once we have it, 3-level, 1 loop and 2 loops, then I think it will be reasonable to make a guess to all loops. What is the whole loop? Asymptotic result. Why asymptotic? Because I think it's probably natural to expect that as you are starting more and more loops, you are starting to do loops and loops and loops, and then you will face the same kind of interesting problems that you face from the spectrum when the number of loops is so large that you start getting so-called wrapping interactions, where the interactions are so long along the spin chain that start wrapping around. And in the spectrum, these were called so-called Lusher corrections. The first time it appears, the first virtual correction that corrects the energy due to this finite size effects, due to this virtual effect that goes around the world. And it's an interesting problem to understand at which loop order will, when will these effects first kick in, either in which loop order or in any other sense, and how to describe them. What is the analog of Lusher for 3-point functions? And what my hope was, and is the following, maybe the following is true. At which loop order do we think that this wrapping correction should appear? So the wrapping corrections for the spectrum, you could say that if you have a twist 2 operator, that the operator has length 2, already at 2 loops you should get this wrapping. But no, it's at 4 loops. And it is delayed. And why is it at 4 loops? Because the operator with size 2 is in the same supermultiplet, it is related by supersymmetry to an operator of size 4. And since for the one of size 4 you could never have corrections before 4 loops, you know that somehow the corrections for the twist 2 must cancel by supersymmetry until you get to 4 loops, so there should be no wrapping corrections. But here you don't have this argument, I think. I think if you have a twist 2 operator here, and here you have other operators, you cannot by supersymmetry just act on one operator and increase its size. So it is possible that already at 2 loops, these twist 2 3-point functions would receive wrapping corrections. It's possible. If so, that would be quite nice, because it would mean the following. It would mean that suppose, using the twist 4 and twist 6 and twist 8 and so on, this length 4 and so on data, suppose that using that data, you could match this table of data here for p to 0. Suppose this is done. So you found the analog of this expression at 2 loops. Suppose this is done. But then you apply it for twist 2 and it doesn't work. It works for twist 4, 6, 8 and so on. But that's great, because then you know what the twist 2 result is, you know what your asymptotic result is, what you have is a prediction for what these wrapping corrections are. So you have again an awesome laboratory for starting to understand what these wrapping corrections for correlation functions could be. So it will not be bad news, it will be good news. It means that already at a low loop order, we have access to this very exciting data. But along with this goes a suggestion that if you try to bootstrap these correlation functions, I would suggest not to try to use the twist 2 data right away. Because we don't know if the twist 2 data is plagued or not by this wrapping correction. It's safer to use first twist 4, twist 6, and so on, this kind of data with these sums of 3-point functions. Even if twist 2 looks much simpler because there is just one solution, one 3-point function, it's a big temptation to use twist 2. I would suggest to use first twist 4, fix this table, and then see, does it work for twist 2? Great, but if it does not, it's because of wrapping. And we should then study wrapping. What about classical limits? Can we take limits where we have a huge number of Bitterroots? Can we take limits where effectively these spin chains that in this lecture we studied them with like 4, 6, 8, and so on. Can we make big spin chains and take classical limits and start getting expressions that look similar to weak and strong coupling? This was another approach that was very successful in the spectrum problem. In the spectrum problem, Kostya, Kazakov, Minahan, and Marshikov, for example, had proposed a set of equations that in the classical limit describe weak and strong coupling at the same time if you just change some parameter. So it was very convenient to have the same description, at least in the so-called classical limit, that was basically universal and valid at weak and strong coupling. And it was very inspiring to have this description, in particular to discretize then the classical result at strong coupling, knowing how the continuum, how it appeared in the continuum limit out of some quantum bit equations at weak coupling. So if you know that you take this, you take some kind of continuum limit and you get some algebraic curves and some Riemann surfaces and whatnot. And at strong coupling, you only have those Riemann surfaces and so on. You can try to engineer and discretize them back. And this was kind of what Arutunov, Frolov, and Staudacher did with these algebraic curves that Kostya and friends have computed. They guessed what the discretization would be, and those were indeed the correct quantum bit equations. So classical limits is another very important source of inspiration. So one is, as I said before, finding these patterns at weak coupling and guessing. The other is these classical limits. And the third one would be a more bootstrap-like approach, again used also in a spectrum problem, when people change and start thinking not about the Hamiltonian, but rather about S-matrix and how to fix the S-matrix for the spectrum problem and so on. So all these three approaches for 3-point functions, they have an analog in the spectrum problem, and we should have all of them in mind. What about beyond leading twists in the OP of 4-point functions? Remember, we had this table of data that we generated for twist 4. We generated all this table of data. We predicted the first line below the diagonal of the twist 4 single trace. We have many more to predict, both at tree level and at loop level. We need to find a way of understanding how to describe the OP of 4-point functions in the planar limit in a way that is friendly to integrability. Because right now, not only we don't know how to describe the other sectors, but we are also worried about double traces, and hopefully we should find a way out. What about more than one operator with spin? We took one operator with spin, we could want to consider more operators with spin. The complication here is that as you take more operators with spin, you start getting more tensor structures. It's no longer true that you get just one result fixed by symmetry. You will get different tensor structures, but okay, who cares? You put operators in spin, you get 5 tensor structures, you compute the 5 numbers, and that's it. But it's definitely more complicated, and it will definitely be very interesting to consider. And probably when you start considering more operators with more and more spin at the quantum level and so on, you can have some hope of starting to connect with other kind of areas where people study, for example, scattering amplitudes, and it is expected that this kind of correlators, for example, of 3 operators with spin, in some particular limit should be related to the 6-point scattering amplitude, for example. This I said already. Is there a bootstrap approach? Is there some way of fixing this F here? And related to that, I should emphasize again that there was this program that Benjamin was recalling, lecturing about for Wilson loops, where the bootstrap approach is very efficient, where we have a bootstrap for many particles, where it takes a very simple factorized form, just a product of pentagons, And we might wonder whether there is some analog here for trying to bootstrap this function f. And in that respect, this other sector, this SU1/1, is particularly simple, because in this SU1/1 sector, recently Caetano and Fleury computed this analog 3-point function, and now these lines are fermions, and they did find a form. And here it's actually a more general case compared to those. Notice that now the 3 operators are non-BPS. And even though I consider the huge generalization compared to the previous cases, the result is simpler. There's really a huge simplicity in this SU1/1. And the result is super trivial. There's no determinants, there's nothing. The result is basically this factor here, that I think is just some finite size effect. There's some length here, so let's ignore this for the moment. And then some products of P operators, they remind very much of pentagon operators, between roots of operator 1 and 2, and between roots of the same operator, 1 and 1, 2 and 2, 3 and 3. Exactly the same kind of factorized form, almost wanting us to think of this operator O3 as some operator and some form factor between these two operators of this third operator here. But of course, we don't know, is this a coincidence? Why is SU1/1 so much simpler? Why is this result so much simpler than what we have seen before? Is there a set of axioms for this P, which is of course the analog of the F's we saw before? I just called it P because it's so similar to the pentagons that Ben was talking about. But this might be another sector where it is possible to make progress. And in this sector, loop correctors are also known because João and Tiago, they computed the splitting operator in SU1/1, so they were not lazy like we were for SL2. They computed the splitting operator, they checked the form of the wave functions, and they found several nice things. They found that, for example, these contact terms in SU1/1 are just constants. They are not complicated functions of the momentum. They are just some very, very simple constants. And this hints at some algebraic description of the states in SU1/1 that is not yet known. So that would be another way of trying to make progress, trying to develop an algebraic description of the beta states that is only known right now for SU2. And both for SL2 and for SU1/1, we have indications that the results are so nice and simple that there should be an algebraic description of the states. This I said already. What about rank 1? What about dimensionless determinant representation? Is there some Weierstrahl-Acker? And there are, of course, many other questions, but I'm running out of